It's supposed to be introductory. We'll see if that's the case. There's going to be a fair amount of maths, so don't be scared off by that. But none of the maths itself is too complicated. So it's supposed to be a guided tour through the landscape of reinforcement learning. But I think perhaps it should be called a random walk through the landscape of reinforcement learning. This is my first ever talk on the subject. In fact, I don't know if you can see at the bottom, a big caveat is I'm not really sure why I'm here. So I was asked about a month ago to give this talk, and when I was asked to give the talk here on reinforcement learning, my answer was, well, I don't know very much about reinforcement learning. To which the person whose name shall not be spoken said, you'll be fine. And so I spent the last month trying to learn as much as I could about reinforcement learning, and this is what you're going to get. So the first thing is actually a question for you. Why are you here? And this is kind of in some way the way we interact with the world. We think about the state that we're in at the moment and where we want to go. And we have some things that we want. We have some, we need food and we need shelter and we need all of these sorts of things. And the way we interact with the world along some lines is to try and figure out the best paths to get those things. We need a job so that we can eat. And we have these sorts of rewards, which are food and warmth and shelter. But along the way, we also pick up other sorts of rewards. And we're going to go into some detail about what we mean by rewards. But you might simply get some pleasure from learning something new. And that might be something which you consider rewarding. OK, so can you read this at the back? Yeah, it's OK? Cool. So the basic plan of this talk, I want to give you the general idea about how reinforcement learning fits into AI as a whole. So, we've seen lots of examples of different types of aspects of AI so far at this meeting, but we want to see where reinforcement learning fits into all of that. Before we go into the details of what it really is, I want to show you a few examples of what it can do. And then in order to really discuss reinforcement learning, the technical side, we need to discuss something called a Markov decision process. And from that, we can define reinforcement learning in a fairly concrete way. And really, the question that we want to answer through all of this is, how do we learn to interact in an environment? Okay? And we're going to specify precisely what we mean by all of that. But we're going to come up with a few methods, or we're going to discuss a few methods, which will allow us to interact with an environment in some sort of efficient way. Okay? These are going to be some exact methods, Monte Carlo, Q-learning, and how neural networks and deep learning in particular fits into reinforcement learning. I'll then talk a little bit about some of the problems with reinforcement learning and the future, sort of where we are at the cutting edge and where we might be, some of the things that we really need to do to progress in this field. One thing I should say is that I am definitely not the expert on these subjects in this room. So if there are questions which I cannot answer, which is quite likely, I'm going to defer to a number of people that I see sitting around here who do know probably more about this than I do. So some of the references for this, so Sutton and Bartow is sort of the canonical text on reinforcement learning. It's a really lovely book, lots of examples, lots of theory. If you go onto YouTube, there's the Deep Reinforcement Learning Bootcamp, which is a series of lectures, and they are really fantastic. And then another YouTube channel which talks about reinforcement learning occasionally, but more broadly about artificial intelligence, is 2-minute papers, where they essentially go through in a very, very short space of time the really powerful results and extremely interesting cutting-edge research in machine learning. OK, so how does all of this fit into machine learning or artificial intelligence more broadly? So we have this diagram here, and this whole diagram is the field of AI. And within the field of AI, artificial intelligence, we have here the field of machine learning, which is a subset of problems within artificial intelligence. In fact, before machine learning came along, there were ideas about expert systems whereby somebody would program a machine which could answer questions, but really the machine wasn't learning along the way. It was very explicitly being given a set of rules about what to do in certain circumstances. So expert systems and sort of ideas within formal logic fit within the field of artificial intelligence, but don't count as machine learning. And then broadly, there are 3 areas that one can think about within machine learning. There's supervised learning, where we can think about simple regression problems. We can think about classification problems. So in the center, we've got this region which is deep learning. And it's not that deep learning is different from supervised or unsupervised or reinforcement learning, but it's really that it's a set of tools that allows you to tackle these different areas. So supervised learning without deep learning allows you to do some simple regression problems, line fitting, fitting very simple functions. Within deep learning, you might want to do classifications on complex images. So this Galaxy Zoo, which was a competition online whereby you were given thousands of examples of pictures of galaxies, and the task was to program a machine learning algorithm which could classify these galaxies into different subtypes. So in these cases, you're always given the labels. Within the supervised learning task, you're given the labels of some data set. But you might want to do something unsupervised where you're not given any labels, but you want to find some sort of structure in your data. So you might think of something like k-means clustering, where you have some data and you want your algorithm to automatically say, there are multiple clusters here. Okay? Data here is similar in some way and different from data here, and data here similarly is similar in some way and different from data in the other regions. Okay? And you can again come up with algorithms which do that explicitly. This idea of generative adversarial networks also fits into the unsupervised learning category, although it's a slightly sort of strange idea because in some sense you do have labels of data, but you're getting a system to generate new images in this case without the particular CNN, for instance, actually having access to those labels. Okay? And then reinforcement learning is a separate realm in and of itself. And within reinforcement learning, you can apply all of the methods that you have from deep learning to these sorts of problems. And we'll see exactly what those are in a moment. So reinforcement learning came about from actually a combination of a couple of disciplines, one of which is from psychology. Psychology was looking at behavior and asking the question, how does an organism, might be an animal, might be a human, learn in some environment? And the answer is very often is learning through trial and error. Okay? It moves within an environment, it has some feedback from the environment, it has some aim, it might want to get food, and it learns to associate those rewards, that food, with certain actions. Indeed, I'll talk a little bit about secondary reinforcers, but what that really means is that you might have some reward. It might be that you're aiming to get food, but there's something else which you find is associated with that food, and that itself becomes some secondary reinforcer. So the other direction was optimal control, where these ideas of value functions, which I'll talk about shortly, and dynamic programming came about. But in some sense, there's no real learning. It's not a trial and error interaction with an environment. So these ideas of trial and error, interaction with an environment, and these ideas of optimal control came together to give us the field of reinforcement learning. So before we actually get on to precisely how one thinks about programming a reinforcement learning system, I just want to give a couple of examples. I'll explain this rather than you having to read it. But this is the DeepMind Q-learning, which was given the task of learning to play a computer game. And all it's given are pixel values. So it's a computer game, pixel values, and all it's asked to do is to increase the score. Okay? It knows nothing about physics, it knows nothing about balls bouncing around, it knows nothing about what it can control, but it's able to perform certain actions. And from our point of view, we know those actions are move this paddle left and right. And over time, it realizes in some sense, that it can increase its score by performing certain actions when it's in certain states. And it starts off terribly because it has no idea what any of this means. And over time, it starts to associate those actions with the rewards. And by rewards, it simply means the increase of this score. So after a couple of hours, it becomes as good as a human player. And a couple of hours later, it's even better than that. And in fact, something rather interesting happens here. It finds a way to optimize its behavior, which is probably different from what a human would find, which is that in this case, it's trying to remove these blocks, and it finds that if it creates a little wedge at one side, then the ball bounces around at the top. It sort of found some kind of bug in the system, and actually it's superhuman by this point. It's able to score much, much better than humans can. The game of Go, a Chinese game several thousand years old, a couple of years ago, again, Google DeepMind, had this program, AlphaGo, which they had developed to try and challenge the world's best Go players. It's a game somewhat like chess, but it actually has a much larger state space than does chess. And the Go community thought this was absolutely impossible. This is such a complicated game. You have to think in such creative ways. It was just going to be impossible to get a computer to do this. They managed to beat one of the top champions, but they thought that the difference between the Chinese champion at the time and Li Sedol, who was the world champion and had been for many years, they thought that this difference between this pretty good player and this incredible player was enough that Li Sedol would be able to beat the computer. But in fact, it turned out that not only could Li Sedol not beat the computer, well, did manage to once, but in a match of 5 games, the computer turned out to produce moves which seemed on the face of it incredibly surprising. There was some aspect of creativity. The way it had worked was that the machine was given 100,000 games of Go taken from human players. It learned from that, and then it learned by playing itself again and again and again to figure out appropriate strategies. And in fact, in one of the games, there was one particular move which absolutely amazed the Go community. It was a move that no human player would ever make. But it actually turned out to be the key move, and such a creative move that it absolutely changed Li Sedol's idea of what machines could do. This move is known as Move 37. So it's worth looking. So there's a very nice video on YouTube that tells you the whole story about AlphaGo. How about if you want to get a simulated person to learn to walk? Well, you create some environment, you create some reward, and the reward is that you can keep walking as long as possible. You program in dynamics, and you allow the system to move around, first of all, at random, trial and error. And over time, it gets feedback from the environment about the best things to do, and you find that, in fact, you can create some fairly complex behavior which allows it to interact with its environment in pretty impressive ways. Not always perfect, but over time, it gets better and better and better. And maybe it doesn't look a lot like a human walking, but that wasn't the aim. That wasn't what it was asked to do. It wasn't asked to try to replicate what a human does. It was simply asked to be able to move as far as it could within this environment. Self-driving cars are another area where reinforcement learning is used. And again, if you go onto YouTube, you'll find some really nice examples where you can actually see self-driving cars learning in real time. Okay? They're put in some environment. By trial and error, you'll see them move the steering wheel, and it moves from side to side, and is given some feedback about how good it did, and then changes its behavior and learns to interact within that environment very efficiently. Similarly, within manufacturing, if you've got robotic systems, reinforcement learning is a way to get those systems to learn to efficiently perform the task that you want them to perform. This is a very simple, kind of clean example, and you can see here, this is the so-called swing-up cart pole. You have some robotic arm, and you have a swinging device, and the idea is that you want this system to learn to balance this pole with a weight on the end of it. Okay? You could imagine that you could do that, so you could have some system with a stick, and you want to learn to balance it over time. Okay? And what the system does is just experiments. It sees what happens when it moves in different directions. And what I mean by what happens is really how good is it at the task that is being given. Okay? And to start with, it's pretty bad. It moves around fairly randomly. Every now and then, it seems to swing it up. And it keeps it there for maybe half a second. But in fact, a few of these iterations are enough for it to learn what are the appropriate movements for it to stay up for an indefinitely long amount of time. So you see here, again, it's doing something that appears pretty random. But from this experience, it's learning about the relationship between the states and the actions. We'll see very explicitly what that means in a moment. So already by 10 seconds of training, it's starting to be able to swing this pole up and actually balance it. And then I think on the next one, it manages to. So just imagine this. Imagine that if you were trying to program in the physics of precisely what is happening here, okay, actually giving you hard and fast rules. If you are in this state, then this is the thing you have to do. Okay? In this particular situation, it might not be that tricky, but if you're in a more complicated environment, it's going to be very, very difficult to hard code those rules in. Although, as those of you who were in the talk yesterday saw, this Boston Dynamics, the robotics group, that's essentially what they're doing. They're not using these systems. They've found that actually reinforcement learning isn't fast enough and accurate enough to be able to move in the complicated environments that they're interested in. Okay. Okay. What do all of these things have in common? Any thoughts? Okay, I can repeat it. So that was the optimal action depends only on the current state. Okay, so this is to do with the sort of Markov idea. So another thing that they have in common is that there is some very clear, explicit goal. Okay, keep the pole swung up as long as possible. Win the game of Go. Get as many points as possible on the computer game. Don't crash the car. Okay, all of these things are fairly explicit and have some way of encoding them into a mathematical expression. And it might simply be the amount of time that it manages to go for performing some task. One of the important points of machine learning is that there's this distinction between evaluation and instruction. Okay, you have some agent, some robot, for instance, moving around in an environment, and what's important is that the programmer or the controller is never saying to it, this is the thing that you are supposed to do. All it's saying is, yes, that worked well, or no, that didn't work well. And that's enough for it to learn how to interact with its environment in a more and more efficient way. Okay? What we're trying to do is to get a system to interact with an environment without telling it explicitly what to do, without giving it instructions. The only instruction is, do whatever you can to increase this score, to increase this reward. In order to talk about reinforcement learning, we need to introduce a few terms. And those terms are those from the ideas of Markov decision processes. Okay? We have some system. We have some person, let's say, some agent that can move around within some system. And that agent, that person can be in certain states. It might start off, person is in bed. That's one state. It might be that another state is having breakfast. It might be that another state is being at work. Okay? And in each of those states, it has a number of actions that it can take. Okay? So the states here are labeled in blue. We've got S0, S1. I've called these ST1 and ST2, and these are because these, in this particular diagram, are what are called terminal states, which means that you can't move anywhere. You can't move to any other state from there. And within each state, we see there are certain actions we can take. Okay, so in terms of the cart pole, this swing up robot, the state is simply the position and the velocity and the angle of motion of the arm. And the actions that the system can take are move left or move right or move left. Given an action, there might be some probability of moving into another state. Okay? So this says that if I'm in state 0 and I perform action 1, then there is a 0.2 probability that I'll end up back in state 0. There's a 0.5 probability that I'll transition to state 1, and there's a 0.3 probability that I'll transition into this terminal state. Okay? So these sort of green-blue boxes are the probabilities that, given some action, I will move from one state into another state. And then the numbers in black here are the rewards that I get for moving from one state to another state having performed some action. And what we have here are the rewards R, which are I, which are a function of the original state, the action you take, and the state that you end up in. Very often the state that you started in is immaterial. What's actually important is simply the state you end up in, and then you get some reward for being there. Okay? And the Markov decision process is made up of these states, these actions, the rewards and the transition probabilities. Okay? And together, all of that tells you about the entire dynamics and model of your system. Okay? We want something more than that. Okay? It's all well and good to give all of the dynamics of the system, okay? The dynamics of some robotic arm that says if you move in this direction, then with some probability you'll end up doing this, and with another probability you'll end up doing that. What we want to do is to define a policy. And that policy says, given that I'm in some state SI, or I've written it SJ, it doesn't matter, given that I'm in some state, what's the probability that I perform some action? Okay? That's really what we want our system to learn. We want it to learn, now I'm in some state, I don't know what happened before, but I'm in this state now, and I need to choose what action to take. The policy says, what's the probability that I'm going to take this action? What's the probability that I'm going to take that action? It might be deterministic. So it might be that in some state, my policy simply says, now move right, or now move left. Or it might be stochastic. It might be that with probability 0.8, I move to the right, and with probability 0.2, I move to the left. The whole aim of reinforcement learning is to try and find this policy which maximizes the reward. We have to be a little bit careful what we mean by maximizes the reward. We'll look at that now. Okay. So in fact, we can come up with any policy here. We can say, you know, if we are in state S1, then we are always going to take action A1, and we'll end up there. Okay? So we can define any random policy on a Markov decision process. So it's another layer on top of the Markov decision process. It depends what our aim is as to what our policy should be. Okay? So it might be that if you start off in bed, then, well, maybe you just want to stay in bed. You don't want to get out when the alarm goes off. Or it might be that you really want breakfast. Okay? And so your action, your policy is going to depend on the thing that you want to aim for. Do you want to aim for more sleep? Do you want to aim for breakfast? Okay? So we need to be very explicit and careful about how we define our aim. This is the reinforcement learning framework. Okay? We have some agent, and that agent is really the decision-making mind of our system. Okay? We can think of a human being as a reinforcement learning agent. Okay? It's got a brain, and it has policies which say, if I'm in some state, then I want to take some action, or there's a probability of me taking some action. Once I perform some action, based on the state that I'm in and the reward that given the state that I'm in, I perform some action, and that has some feedback on the environment. Okay? It might have some feedback on me as well, and in fact, within reinforcement learning, the body of the robot counts as part of the environment. Okay? So the robot itself might move to some different place. And having performed this action and gone into some new state, the environment also gives some reward back to the agent. It says, okay, you get some number of points for having moved from this state into that state, having performed some particular action. And all of this feedback comes back, and we can think of this either as a discrete process, or we can think of this as a continuous process. But it's this cycle. The agent has a policy which decides, given some state that it's in, what's the action that it should take. Okay? And the aim then is to figure out how should it best explore the environment in such a way that it can come up with a policy which is optimum for increasing its reward. We can ask the question, does the world really seem like a Markov decision process? So one of the important points in a Markov decision process is that the history doesn't matter. Okay? It doesn't matter what state you were in previously. All that matters about your transitions is the states that you're in now. Okay? There's no history. Okay? Or at least there's no memory, I should say. Once you're in some state, there's no memory about where you were in the past. So the actions that I take are purely related to where I am now. That doesn't seem very much like the real world. Okay? Whether I have breakfast is sort of dependent on whether I had breakfast before. Okay? So we can think that actually in the real world, past states do matter. However, the state that I'm in now might be a state where, sure, I might have had breakfast back then, but my state now is one where I have the memory of having had breakfast. So in fact, one can define a Markov decision process such that the memory of past states is actually part of the present state. Okay? So once I have moved into a new state, the fact that I've had breakfast becomes part of my new state. Okay? So actually, we can sort of include memory within a Markov decision process just by including that information in the new states. The world clearly also has lots of state information which is hidden. Okay? As we move around the world, we don't know what's happening the other side of the wall. We don't know what's happening in other people's brains. Similarly, in a robotic system, the robot isn't always going to have information, perfect information, about what's happening in the world around it. One can define something called a partially observable Markov decision process. a POM DP. Also, the world is continuous, and what I wrote before looked like it was some fairly discrete set of states and some discrete set of actions, but one can also define continuous state Markov decision processes. Okay, so this is vital. We need to understand this idea of the reward versus the value of being in some state. Okay. Let's think about some path through a Markov decision process. Start off in some state, we take some action, we move into another state, we take another action, we move into another state, and we can think of some trace through time. So this tau is often called the trace, or the path through the Markov decision process, and the total reward is the addition of all of the rewards that it gets from the first step that it takes up until some terminal state. And I can just write it as a sum like this. Okay, so I can think of defining my total reward as just the addition of all the little pieces of reward that I get as I go along. Who has heard of psychic secretion? So psychic secretion was the term that Pavlov gave to the salivation of the dog when it heard the bell. In fact, the real story is slightly more complicated, but there's this idea that you have a dog, and whenever it sees food, it salivates. But if you start to ring a bell a little bit before you give it the food, then it starts to associate the bell with the food, and it doesn't start to salivate when it sees the food. It starts to salivate when it hears the bell. What that means is that although the food is really the reward here, it sees some value in the bell. It sees value in the bell because it's associated with something that has a very explicit reward. Okay? So reward tells us about the value of states, but it might be rewards into future states that tell us that actually there might be some reward coming, okay? And it gives value to where we are now. So we're going to deal with a very, very simple Markov decision process. It's sort of like a maze. Okay? It's a very simple maze. We're going to start here, and we want our reinforcement learning system to be able to move around this maze in such a way that it gets to this terminal state, where once it's in this terminal state, it takes any action, and then it gets a +1. Okay? There's also this negative state, which is another terminating state. If it gets there, then it doesn't get a reward when it's in that state, but the next action it takes, it gets a -1. Okay? And there's some square here that it can't move into at all, and it can move around like this. If it tries to move down, it's going to bounce off the wall. If it tries to move up here, it bounces off the wall, and it remains in the same state. Okay. So the only rewards here are the +1 and the -1. So to define a value for any state, we have to have a policy. Okay? Because it could have been that with the bell, that bell isn't actually associated with the food in the future, and then the bell wouldn't have any value at all. Okay? We can generalize a little bit. So I said before that the total reward was just the sum of R1 plus R2 plus et cetera, up to some terminating reward. Okay? And it might be that many of those rewards are 0. Okay? We can define a discount factor. This discount factor is this gamma, and it's a number between 0 and 1. And what it means is that I care more about rewards that I get soon than those rewards that I get later. Okay? And this has a number of reasons. Okay? For a start, it means that if we've got some sparse reward in a space like the grid world, as that maze is called, we get by having this discount factor, the number of steps you take to get to that reward means that that +1 gets less and less valuable, less and less important, the further it is into the future. So if our system wants to increase the total reward that it gets, well, it wants to get that reward as soon as possible. Okay? This t here, which is some discrete number, some integer, okay? Each time step into the future, this gamma to the t is going to be decreasing. Okay? So we can think that the discount factor just says all rewards in the future, the further into the future they are, the less important they are to our value here. Okay? So it might be that we have the option of having lunch now, or there's some huge meal, but it's a long, long way in the future. Okay? You have to balance the fact that there's a bigger reward in the future, smaller reward now, but the one in the future may be more uncertain because there may be some probability of getting there, given your policy. So that's a balance that one has to calculate. What do we want to do? The aim of our policy, we want to find the policy which maximizes the expectation value of this total reward, this discounted reward. Okay? So we can move through some path in our Markov decision process, and the path that we take is given by our policy, and the policy is pi, and we want to find that policy which maximizes the total expected return, okay? The addition with factors of gamma of our rewards. Okay? And it's conditioned on the policy, because the policy tells us, given that I'm in some state, what's the next action that I'm going to move into. I spoke about the difference between value and reward before, but now we can talk about it explicitly. Okay? In fact, the value is precisely the value, given some policy, of being in some state is the expected return, in this case discounted, given that I start off in that state, and given that I'm taking actions under this policy pi. Okay? So what this says is, if I want to calculate how valuable the state I'm in here now is, okay, I need to think about what my policy is. Okay? My policy tells me what's the path that I'm going to take through this Markov decision process, and therefore I can calculate the value in this state. Okay? If I'm in a different state, I'm going to have a different value. If I have a different policy, I'm going to have a different value, because it might be that my policy says, always go to the right. Okay? In which case, if you start here, the value of being in this state is going to be 0 under the policy, always move to the right. Okay? However, in this case, we can see very simply, we'll come on to that in a moment, we can see very simply what the obvious policy should be. Okay? Our policy is going to be, well, we can move up this way and move across there, or we can move that way and move across there, and you have to work out, given the discount factor, what's the shortest path. Okay? And we'll see in a moment a way to calculate that. So if you know the value of your states, which is what that previous expression calculated, we can calculate the policy, and the policy is going to be, I always want to move into the next state which has the most value. Okay? That's how we move through our environment. But what that means is that our policy is dictated by the values, but the values themselves are calculated by our policy. Okay? So we have a bit of a vicious cycle here. The policy defines the values. We saw V was conditioned on a policy, but the values themselves are calculated by the policy. Okay? So we have to be a little bit careful here. How do we solve this problem? So in this case, the solution without any discount is trivial. We can calculate the value, given that we already know precisely what the obvious policy is. Okay? In fact, in every state, without any discount, the value is 1, because the future return, because I definitely want to get to that point, the future return is 1, so the value of every state is 1. If I include a discount factor of 0.9, then for every step away from that reward, there's going to be a factor of 0.9. So the value of this state here is just 0.9, because I know that in the next step, I can take myself to a state where actually the reward in moving from that state is 0.9. And we have to have another factor of 0.9 everywhere we are. Okay? But again, this is conditioned on the fact that we already know what our policy is. We know what our policy is because we know how to move around mazes. What we want to do is to have a system which can learn this for itself. Remember, there was something extra in the Markov decision process that we need, which is the transition probabilities. Because it might be that if I'm in some state and I say, I really want to move to the right, it might be that I'm rubbish at moving to the right and I end up moving to the left. Okay? So the transition probabilities say, given that I'm in some state and I perform some action, what's the probability of ending up in another state? Okay? And that might not be 1, okay, for the state that I want to end up in. So let's take a stochastic system where actually there's a probability of 0.7 of moving in the direction that I want to go. And there's a probability of 0.1 of moving in all the other directions. Okay? So I could then think about calculating the value of this state, and I call this S22 here, given that I know that I really want to move right. There's a discount factor here, and then because I know that I get a reward of 1 for being in that state, I get 0.7. Okay? It's an expectation value. So what I'm asking here is, what's the expected return? So there's a 0.7, because with probability 0.7, I do end up getting that 1. With a probability 0.1, I end up moving to the left, okay, to this state S12, whatever the value of that is. Okay? I don't know what it is, okay? But I have to add that onto my value now. So discounted 0.1 probability of whatever the value is of state S12. Similarly, S21, and in fact, it could be that I try and turn right and I end up moving up, and I bounce off and I come back to this point here. So I have to add on the value of this same state. Okay? So in this way, again, if I know what my policy is, I can calculate the value. It's some coupled set of equations, but at least they're linear. But importantly, in order to calculate this, I needed to have some policy. And this looks like this is going to be a difficult problem because, again, the policy is informed by our values, and the values are defined by the policy, so we have a problem. So remember, the value of being in some state, given a policy pi, is the expectation value over future rewards. Let's see what we can do with this. Let's just split off the first reward, the reward for the first step. Whatever that is, it's the reward for being in state, for moving from state S0 to S1, performing action A0. Okay? And add on to that the rewards for all the next steps. Okay? So all I've done is taken that sum, and I've just taken out the first term. Okay? I've got a gamma t here, all of this stuff here. But in fact, this expression here, to the right of this reward, when I take the expectation value, and I can take here the expectation value of the sum as the sum of the expectation values, in fact, I don't even need to at this stage, is that in fact that's the value of being in state S1. Okay? So the value of being in state S is the expectation value of the reward that I get in the next state plus discounted value. Now I can write that expectation value as a sum. I can sum over future states and the actions which are dictated by my policy. Remember, the policy is just what's the probability that I'm in some state S and I perform some action. Okay? And I end up with this coupled equation. It's a coupled equation that has v on one side and v on the other. They're both just functions of S. This one is summing over S prime, and that's just S there. Okay? This is known as the Bellman equation. This is sort of the fundamental equation within reinforcement learning, which originally came from optimal control, okay, but allows us to talk about the relationship between v and pi. It gives us some coupled set of equations. How about optimality? So what we're really trying to do is to find the best policy. We're trying to find the policy which gives us the most reward over time. Okay? And it's simply that which is, whenever we're in some state, we just want to take the action which maximizes this expression. Okay? And the star here one generally uses for the optimal policy. Okay. So now we're going to come up with our first method of actually calculating an optimum policy. Up to now, we've said, well, we know what our agent is going to do. It's going to move around in a particular way. But how can we actually calculate that? Well, it turns out that we can calculate it precisely from this Bellman optimality equation. The way we're going to do that is to say, my first guess is that the value for everything is 0. Everywhere it's 0. Okay? But I'm going to update it. I'm going to perform an iteration, something called a value iteration. So I say that v star, the 0th iteration for all states is 0. And we're going to update it using the Bellman optimality equation, where for the values, I'm going to use the previous values that I guessed, which were all 0 everywhere. Okay? And I'm going to let that update to my new expected values. Okay? And the reason for this is because the values that I have now are associated with future rewards and the values of states that I can get to from around me. Okay? So that's really what this equation is saying. This one here, the value of the state now is simply equal to the reward I can get to moving into some state plus the value of that state. The value of that state is associated again with rewards and values of future states. And we can iterate this. We start with 0 value everywhere, and we iterate this procedure to end up getting some optimality. This is really the procedure. Every time we just iterate again and again and again to update our values at every state based on the Bellman equation. In fact, the Bellman optimality equation. We always want to maximize over the action. So what we're going to say is, I'm in some state. I could move that way. 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 What happens if we maximize this? Find the action which takes us to the maximum next best state. with a reward. Okay. Having done that, it turns out that this converges. In fact, it converges to the optimum value. Okay. And having found the values of all of our states, well, the optimum policy is very simple. It's just do the thing that takes you to the next most valuable state. Okay. This knows nothing about the policy, but it turns out that because we have this maximization here, it does give us precisely the optimum value function. And from that, we can read off the optimum policy. Okay. It turns out that you need an infinite number of steps to converge, but if you want some epsilon away from the optimum value, then you can always stop this after some time. Okay. So, how are we doing for time? Okay, we're all right. So let's see now how this would work for the grid world. Remember, the first thing is that we set the value to 0 everywhere. Okay? Value everywhere is 0. On the next time step, what we're going to do is we're going to calculate our values based on the previous values, which are all 0, plus any rewards that we might get. Okay? And remember, it's an expectation value, so we have to, again, maximize over the action, i.e., what's the best action? I could move in these different directions. What's the best action I could take? What does that give me in terms of a value? And what that turns out is that, well, everything is still 0 because to move from here to here, okay, you get no reward. The only value that we get is ending up with a 1 here and a -1 there, because remember, the Bellman equation told us that the value, the update value, is equal to the reward that we get from moving it to the next best state, plus the value of that state. But all the values are 0, so the value that we get on this iteration is just 1 and -1. We can repeat. And what we find is that this value propagates itself back through all the states. Okay? All of these are still 0 because they don't know anything yet about the value that is coming from the reward. I recommend doing this calculation. Okay? It's a very simple bit of programming, but just set up the Bellman optimality equation, set all your values to 0, set the transition probabilities, so the transition probabilities are 0.7 of doing exactly what you wanted and 0.1 of not doing what you wanted. So here, we've got a value at this point of -0.09. That seems really weird. Why would we have that? Well, we know that we want to move up here. But remember, the value here is associated with the optimum movement. So the optimum movement is to move to that square there. But we might accidentally, because we got 0.1 probability of moving right, we might end up there. And so in fact, the fact that there's some value here, negative value, influences what's happening here. Okay? This isn't such a great state as that one, because we might accidentally move into the negative reward space. And you iterate again and again and again, and after some iterations, you end up with these as your values. Okay? I think this was about after about 30 or 40 iterations, it settled pretty nicely on these values. Now we have values for every state. Okay? This has value 0.26. Why does it have value 0.26? Well, because it's next to a square which has slightly higher value, which is next to a square which has slightly higher value, which in the end is next to a square which will give us some reward. Okay? So being in this state itself has some value, because we know that if we take the optimum policy, okay, we can end up with this in the state where there is actually a reward. Okay? This is, remember the difference. There's no reward for being here, but it has some associated value, because from this state we can get into a high reward state. We can do something similar. There's another process we can take. So what we did there was value iteration. We started off with some terrible value, 0 everywhere, and we iterated using the Bellman optimality equation. Okay? And we eventually converged onto some set of values where, given that set of values, we can now write down our policy, which is always, whenever I'm in a state, move to the next state which has the highest value. Okay? We can iterate our policies. Let's take some random policy. Okay, it might be a terrible policy. Given that policy, we can calculate the value of all the states. Okay? The policy just says, what's the probability of taking some action A given that I'm in some state? I can calculate the value of all states given that policy. Given that value, I can then say, so now I've got values everywhere. I've calculated values everywhere for that given policy. Now, given those values, I can say, okay, I'm going to change my policy. And my policy is now going to be, now move into the state which has the highest value. Although that's the values that I just calculated from the previous policy. But it turns out, again, because of the way the equations, the Bellman equations work, this iteration procedure, I'll give you some policy, you work out the values of all the states, from those values of the states, calculate a new policy, which might actually be now, okay, before you said you were going to move forwards, and we calculated the value based on that, now actually we realize it's best to move right. Okay? We perform this iteration, and it turns out that, again, this converges. So you can do two things. Well, you can do a number of things, but one of them is you can iterate over the values. That will take you to the optimum values, or you can iterate over policies and values. Okay? And that, again, will converge. There's something really important about all of the things that we've done here. In order to calculate these values and the best policies, we really needed to know the transition probabilities. I told you that with probability 0.7, you do exactly what you want to do, and with probability 0.1, you don't. And we also knew what states we ended up going into, and we knew what rewards we got. Okay? What that means is that we knew the model of the environment. To know the transition probabilities says that we know everything there is to know about that Markov decision process. Okay? That's not usually the case. Okay? If we have some system, some agent, and it's in some new environment, we don't really want to have to tell it about all the states and all the transition probabilities and all the rewards. What we've shown up to now is really optimal control. Okay? All of the language about these value functions and the policy is the same within reinforcement learning, but the fundamental improvement of reinforcement learning over optimal control is precisely that we want our agent to explore, and none of that's happened here. Okay? We've got some closed exact method. In fact, they're called dynamic programming methods. We've got some exact method to precisely calculate the value and the policy given some environment. But I've given you the environment exactly. What we want to do now is to say, okay, I'm not going to tell you about the environment. You're just able to sample it. You're able to move around it. And from that, I want you to figure out what's the optimum policy. It turns out that there are some good reasons occasionally to use these dynamic programming methods. Okay? But if we want to understand all of this, we need to understand the values of every state. Okay? When we have some small state space, like the Markov decision process I showed before, that's fairly easy. We take a fairly simple game like Tetris. So Tetris is this game where you have falling blocks on the screen, and you have to rearrange them such that they all line up nicely at the bottom, and you form rows, and once you form a row, they disappear. Okay? Turns out there's about 10 to the 60 states in this very simple game. Okay? If you want to calculate the Bellman equations for 10 to the 60 states, well, good luck. Okay? It's not going to be the way to do it. So what we want to do is to find a way to explore our environment. One way to do that is with a Monte Carlo method. Okay? What we can do is to say, I'm in some state here and I want to find out its value. And I've got some policy. And the policy tells me about what I'm likely to do in certain states. Okay? And I'm going to calculate the value of this state simply by following some path through my Markov decision process. Okay? And picking up rewards along the way, that's going to tell me about how valuable that state was. Because it might be that I find that, given some policy, I move in some direction through the state space, and I pick up rewards along the way, and I go, okay, that was actually a pretty good place to start. Okay? And I go back and I go, okay, the value of this is whatever I found it as. Okay? That's using some particular policy. I then go to another state, and I say, okay, what's the value of this? And what's the value of this state? And what's the value of this state? But really, I want to do this again in an iterative procedure. I can calculate the value of every state, but that's based on a policy. Now, having calculated the value of a few states, I can update my policy and say, well, before I thought that this was a good idea. Now I realize that actually, because I now know a slightly more accurate estimation of these values, maybe I can change my policy. Maybe I shouldn't move in that direction, maybe I should move in this direction, because I've just found, by exploring the space, that actually this state is more valuable than the one that I went to previously. To get on to the interesting ideas of Well, this is slightly out of order, but that should be okay. To get on to the more interesting ideas of reinforcement learning, and we'll come in a moment back to the Monte Carlo, we need to define something called a state action value. Okay. Previously, the value was simply, how valuable is this state, which said, what are the likely future rewards, the total rewards that I'm going to get from moving from this state given some policy. Instead, what I can define is a state action value, which doesn't say what's the value of this state, but says what's the value of being in this state and performing some action. Okay? So now it's just a function of two variables. Previously, we had v as a function of s. Now I've got q as a function of s and a. Okay? And it turns out that sometimes this is actually a more useful thing to have. So remember, the Bellman optimality equation before was that the value of our optimum policy for some state was maximizing over a, that is to say, always take the best action that's going to take you into the next state with the highest value, okay? Given some transition probability. Now we have a similar thing for q, but here, interestingly and importantly, we don't have to maximize over a. Okay? Because we've already said it's just a function of a. So for each of those actions that we can take, a is built into it. Okay? So what that means is that we no longer have a single value for each state. Now we have a value for being in this state and moving right. Value for being in this state and moving up, which will take me back to that state. Value for being in this state and moving left. We can use a Monte Carlo method for calculating q. Okay? And the Monte Carlo method you can think of in this case simply as a simulation. Okay? We're just going to run through some potential path through our space given some policy. Okay? So remember, we want to calculate q as a function of state and action given a policy. So we start in our state S and take action A, and then we just follow our policy. We repeat this again and again and again, and we average the returns. And those returns become the value of q given pi of S and A. There's a problem with this, though. If the policy is deterministic, and the transitions are deterministic within the environment, then each time a state is entered, only one action A is ever going to be taken. Okay? And only one path is going to be explored. What we really want to do is to explore lots of different paths. There are a couple of ways to do this. So in fact, just running through this. So we have some policy, we'll call it pi 0. We explore, we run over multiple episodes. We say, okay, we're going to start in some state, S. We're going to calculate the potential future rewards. We're going to then tell ourselves what that value of q is, but we're going to perform this over multiple episodes so that we can average if it's not a deterministic system. That then gives us some new q. In fact, it's the state action value of pi 0. We then take that state action value and say, okay, what would the policy be if we followed precisely where the highest values take us? Okay. Each time the policy, actually this isn't quite the right way of thinking about it, this is if it's deterministic, the policy of our state is just take the action which is the maximum value of q in some state over all the a's. Okay. And we iterate that, and again, one can show that this converges to the optimum policy. So what I was trying to do here was to calculate the q values. I want to calculate the q values because given the q values, I can calculate the policy. But in order to calculate the q values, all I really needed to know was, what sort of values can I get from moving from that state in the future? So it actually turns out that I can use one policy for updated from my q values, and I can use another policy for exploring. Okay, so this is the difference between what's called on policy and off policy, and I'll talk about that in more detail a little bit later. In order to overcome the fact that this might all be deterministic, I can throw in some non-determinism. Okay, that's probably a slightly funny way of putting it, but what that means is that I can, most of the time, take the action which is the highest action. But with some chance, epsilon, I might take a different action. Okay? A greedy policy is the one that says, I always want to take the action which is to the next best state. Okay? But in doing so, you might never explore the other states that your policy says, oh, you probably shouldn't go down there, but it might be there's some nice rewards down those paths. Okay? So with some probability epsilon, which you can build into the system, you don't take the highest value state, you take another one. Okay? So this is called an epsilon greedy policy. So it's the difference between a greedy policy, always take the highest value states, or the highest value action for being in a given state, or epsilon greedy, which is occasionally explore off. So it's a difference between what's called exploration, when you have some finite epsilon, and exploitation, which says I always want to do the thing that I think is the best thing to do, even though it might not be. So now we've seen, well, I guess 3 methods. We've seen value iteration, which allows us to calculate the optimum value. We've seen policy iteration, which is the cycle between policies and values. We've seen Monte Carlo, and now we're going to look at something called temporal difference learning. Temporal difference learning is sort of the foundation of many of the modern ways of performing reinforcement learning. And the way to do this is that rather than in Monte Carlo, I started in some state, and I went all the way to the end to some terminating state in order to figure out what the value of this state here was. Okay? In temporal difference learning, I'm just going to take one step. Okay? I'm going to say, this is what I think the value of this state is, based on what I think the state value, based on what I think I might have around me. Let's take a step in some direction. Okay? Take a step in that direction. And the question we ask is, how surprised am I? Do I get some reward that I wasn't expecting? In which case, if that's the case, I can go back and go, actually, this state was more valuable than I thought it was. Okay? Temporal difference learning says, I'm going to go one step down the line in time, and I'm going to look at the difference between what I thought would be here and what I actually find here, and then I'm going to update my previous guess, but I might update it. I'm not just going to update it with that difference between what I thought was going to be there and what's really there, because I might want to explore all the other states around me. Okay? It might be that there are other actions that I can take. So I'm going to have some learning rate, some alpha, which tells me how much I want to update my previous state action value based on the surprise that I have. So let's look at this. So this is called SASA, and that stands for state action reward state action, because that's essentially the set of steps that you're taking. So we're going to start with some arbitrary Q. See? Some Q values for all states and all actions. We're going to choose some initial state, and then from Q as a function of S and A, we're going to choose an action. So I'm in a state, I look at my Q values, and I'm going to choose an action to take. And I'm going to choose it epsilon greedily, which says most of the time take the action which is best, every now and then take another action. Okay? I take that action, and I end up in a new state, and I might find that there's some reward, a reward for moving from state S into this new state, having taken action A, and I'm going to end up in some new state S prime. So this is what the environment returns. Okay. I then define some target, which is a function of this new state S prime, which is just the reward that I get here, plus the Q value that I had already defined here. That's my target. I'm then going to update the state that I've come from. Okay? And I'm going to update it with some learning rate alpha, which says this was the previous value that I had, Q of K, which is just the iteration of state and action. And I'm going to have that with some importance, 1 minus alpha, and I'm going to update it slightly in the direction of the reward that I found. Okay? So again, as I say, this is what I think the value of being in this state and taking this action is. Let's take that action. We find a reward, maybe it's a surprise, maybe it's not, and we update our previous estimate of the Q value by how surprised we are. And we use alpha as our learning rate. Do we want to update it a lot? Do we want to update it a little? Okay? And as you do this iteration, it might be that you start off with some large learning rates, and then you go down to some small learning rate, because once you're beginning to optimize, you don't want to be moving too much into the directions of lower Q values. Q-learning, which you would hear about a lot if you read the reinforcement learning literature, is a pretty simple adaptation of this. Okay? In the previous example, very importantly, the target that I calculated was the reward for moving into the next step, plus gamma, which is the discount factor, times Q of K prime and S, of S prime and A prime. And this A prime was the action from the next step given my policy. So I've already defined some policy. So I want to update my current state action value. I say, okay, perform some epsilon greedy move. I move into a new state. If I find a reward, great, it's going to update. And I'm also going to update by the action value here, given that I'm taking my greedy policy, or epsilon greedy policy. And I'm going to update like that. Or I can do something which is off policy, which says that previously that Q was the Q which the policy told me I should do. Now I'm just going to take the maximum policy. Okay? That is, say, I move into some new value, into some new state. I have a load of different actions that I can take here, and I'm going to take the Q value, which gives me the highest Q. Or I'm going to take the A prime, which gives me the highest Q, and I'm going to update based on that. Okay? This is the fundamental idea of Q learning. There's a problem here. Do you all see a problem here? Okay, I spoke before about Tetris, which had 10 to the 60 states. If I have 10 to the 60 states and I have all of these actions that I can take, I'm going to end up with an enormous table. And that's really inconvenient. Okay? If we have a really big table, then it's really difficult to store this in anything. Okay? We want to store all of the state action values in our computer. And actually, maybe we want a simpler way of doing it than having an enormous table. Is there some way around this? What we really want to be able to do is to approximate our Q. Okay? We've got 10 to the 60 states, and we've got all these actions that we can take. So for each state and for each action, we have a Q value. Okay? That's a lot of Q values. Moreover, if we're moving around in our environment, what happens if I've never been to some state before? If I've never been to this state before, then I have no idea what the Q value is. Okay? So not only do we want to be able to approximate our Q values, rather than having 10 to the 60 times, I don't know, however many actions you have in Tetris, I guess 3. What we want to be able to do is to approximate that, and we want to be able to generalize. We want to have some function which can say, I've never seen this state before, but it looks a bit like that state. Okay? And that can inform me what my policy is, even though I've never seen the state before. How can we think about function approximation? Okay? Here I've got Q, which is a function of 2 values, S and A. Okay? So therefore, the number of values of Q is the number of values of the number of states times the number of actions, presuming you have the same number of states for actions for each state. Instead, I could take some basis of functions, some function f0 of S and A, and that might be, some quadratic, if we're thinking simply about some continuous set of values. This might be a linear function, that might be quadratic, that might be, cubic. Okay? So I can think of simply approximating this by a set of functions with some parameters, theta 0, theta 1, up to theta n. Okay? Q is just a function. It's a function of 2 variables. Okay? But the number of different S's and A's we have is problematic. So if we can find some sensible set of basis functions, then I can reduce the number of parameters I have to just these thetas. So if the number of basis functions is much less than the number of state action pairs, then I've won. Okay? So long as these functions, when we add them up, can be a good approximation to the actual real Q values that I have. So we can do it like that, as I showed before. We can add up some set of functions, or I can think about using a neural network. A neural network is just a function approximator. Okay? With a neural network, I input some numbers, and I output something. So I can think about that as approximating my Q value. A Q value just takes in some state and some action, and those might just be a vector. So for instance, the set of states might be simply some position in some high-dimensional space, and I can input that as a vector, and I can input the state also as a vector. It might be that I've got the left is 1, 0, and right is 0, 1. I input them, and I've got some set of weights here and some activation functions, and at the other side, I get a number. Okay? And so long as there's enough depth, enough generalizability within my neural network, I can use that then to approximate my Q value, or all of my Q values. Deep reinforcement learning, then, is the application of deep neural networks to approximate Q values, or policies. Okay, I'll show you at the end how we can also think about approximating policies. Cool. Let's look again at what Q learning means. Q learning says, start with some arbitrary Q, choose some initial state, choose an action A using our greedy policy from Q. Take that action, we end up in some new state, we calculate a target. Okay? We define this target like that, and we update our Q. We are updating our function, and we know precisely how to do that using a neural network. The output of our network is going to be the Q value that we thought we were going to get, okay? But we can actually take a step in our environment, get some reward, okay, and work out the difference. What's the difference between the reward that we got plus the Q value there and the reward that our neural network told us? It's going to be some difference there. That difference we can then propagate back through the neural network in order to update the values. Okay? All we have there is gradient descent. We have back propagation using some simple gradient descent. Okay? We back propagate in order to update our theta values, which now those theta values are the weights within the neural network, and that allows us to take Q learning, which previously was this update rule with some alpha, and now is just back propagation. Okay? Deep Q learning, which is actually the process that was used to solve that Atari game, the one bouncing the paddle up and down. Deep Q learning is simply the process of using a deep neural network to learn an approximate Q function. So what I just told you was that we could use our neural network to approximate Q. So what that says is, given some state action pair, pass it into the neural network, and that's going to tell us what the Q value is. Okay? And we can calculate the different Q values, and we can then work out what our appropriate policy is. Or we can think about having, instead, a neural network, which we add in, we pass in our state, just our state, and it outputs the probabilities that we should take one action versus another action. Okay? So we can encode either the Q values, or we can encode the policy itself in the neural network. Okay? The value function then, our J of theta, which here we write as the expectation value over some path in the space, given some set of parameters theta, those thetas are the parameters of the neural network, and we sum over the time steps. It turns out that to calculate the gradient of this object, which we need for backpropagation, okay, actually what we need is this slightly complicated, but actually not too tricky to calculate, expression here, which is the derivative of the logarithm of our policy. Okay. Our policy, remember, isn't saying, given some state, what's the action to take. Our policy is, given some state, what's the probability of taking an action. The way we should think about this is the following. We perform some experiment in our environment, and we get back some reward. Okay? We say, what did our policy tell us we should do? Well, it was fairly sure that it should do this, and it was fairly sure that it shouldn't do this. We can think about this as the cart pole problem. We're trying to balance something. Okay? We have some experiment randomly moving around, and every now and then it manages to keep the pole balanced. Okay? So there's some high reward, because it performed the task well. But it said with 80% chance, I wanted to move right at this point, and with 20% chance, I wanted to move left. If the reward was high, what you want to do is to move in the direction of being more sure that indeed you should have moved right. Okay? The reward was high, so we said you did the right thing, but it wasn't too sure about its policy. Okay? Gradient descent in this case, called gradient ascent in this case, is aiming to make the neural network more sure about the action that it took, which ended up giving it a high reward. Okay? In order to do that, you need to work out the cross entropy between the probability that it had for the particular movement and surety. Okay, I'm not going to go into the details of that. Okay. Now, in the last minutes, I'm going to skip through these. There are many other, I've only written a few. I was actually planning on writing a few more here. There are many, many algorithms for reinforcement learning. TD lambda, which says don't just take one step into the future, take a number of steps, okay, and propagate back. which is sort of in between this SARSA algorithm or Q-learning and the Monte Carlo method where you go all the way to the end of the episode. Actor-critic methods where you have both a policy network and a Q network and they sort of inform one another. Double Q-learning, A3C, which is some asynchronous way of having this actor-critic method. There are many, many different algorithms. But what I do want to tell you about perhaps is some of the cutting edge of Q-learning in this minus 1 minute. Okay, I will just tell you that on Saturday, it wasn't DeepMind. So DeepMind is the organization which has done extremely well in getting computers to learn the Atari games, created AlphaGo and AlphaZero, which is sort of a slightly more general purpose algorithm which can play shogi and Go and chess to superhuman levels. But this OpenAI team managed to beat the world champions of this game, Dota 2. If you go on YouTube, well, I imagine you will be as confused as I am unless you've played this game. You will see the most unbelievable chaos going on the screen, but what they've managed to do is to write an algorithm which can beat the world's best players at this game. This is very important because these are not Markov decision processes in the same way that we saw before, because there's lots of hidden information here. There's lots of hidden information, so it's partially observable in that sense. There's lots of information that you don't see about the true state of what's going on around you. Okay? And then I think just to leave it perhaps with this, how does reinforcement learning work in humans? Okay, so I've said all these things about exploration and updating your Q values and working out what the next step was and then iterating backwards. And that's not really what we're doing most of the time as humans. Okay? We do have a model of the world. Okay? If I give you an Atari game, you do know roughly what's going to happen if you press left and you press right. You do have a model of the dynamics of the world. In many of these systems, at least the secondary systems that I told you about, there was no model of the world there. There was no mention of the transition probabilities. They were given to us by the environment, so the environment said, okay, you're going to move into this state. Okay? But there was no internal model within the reinforcement learning framework about what that model was. Okay? Without a model, it's very difficult to understand causality. It's very difficult to understand cause and effect. And of course, the way we interact with the world is by planning into the future and figuring out, given our world model, precisely what the likely events are going to be. Okay? So somehow we need to build this into reinforcement learning frameworks. The other thing that we do is that we can learn one skill. Okay? We can learn to, I don't know, cook one dish. And by learning to cook that dish, if I give you a recipe for another dish, well, you don't need to learn cooking from scratch. We're able very efficiently to transfer knowledge from one domain to another. Okay? So this idea of transfer learning is also extremely important in the future of reinforcement learning. Okay. So I'm just going to finish now with thanks, of course, to the organizing team who have done an amazing job over the last few days. This is really an exceptional school to come to. I'm incredibly impressed both by the organization and by the people who have come here. The conversations I've had have been fantastic. And also to Tali and Seb, Zipalele, Jeremy, Yelisa, and Dean, and probably some others with whom I speak a lot at the UCT RL discussion group. And thank you to all of you for bearing with me in my first ever talk on reinforcement learning. I guess there's not much time now, but I'll be happy to answer questions offline if needs be. So thank you very much.
Thanks for the amazing talk. I know you're very new to this, but in your research in preparing for this, did you come across any applications of where reinforcement learning was used on like a social network scale or I mean, more in like social graph theory kind of setup?
The answer is no, I haven't. But those in the room who know more about reinforcement learning than I do, Dean, do you know of any examples where it's been used in sort of social network theory?